Okay, so we are next going to start the sixth chapter, linear transformations, and in doing so, let us recall something we have already seen before. Suppose that V and W are vector spaces over some field F. Then by this symbol we mean the set of all vector space homomorphisms from V into W. That is, the elements in this set are functions like this from V into W, which are vector space homomorphisms from V into W. No further restriction is imposed on these functions. That is, we are not saying that they should be one to one or on to, nothing like that. They are just simple vector space homomorphisms. Now we have already seen that this is not simply a set but is itself a vector space over the same field F under two operations which we have already defined like this. Let us recall those operations also. Now we will need them. Suppose we consider two elements here. For simplicity, we have decided to omit this F. If the underlying field is understood, then we can just not write it. Then for two such elements, we have defined their sum to be that function from V into W whose definition is given like this. If you apply this function on a vector V coming from V, of course, because we want this to be a function from V into W, then that is defined to be equal to the T1 image of V plus the T2 image of V. Okay, and we have seen that under this operation, this set is an abelian group. And if we take a scalar alpha from the field, then we have also defined this scalar multiplication or multiplication by scalar. You multiply T1 by alpha, and that also is going to be a function from V into W, which we have defined like this. When you apply alpha T1 on a vector V coming from the domain V, that is, here it should be the domain, then by definition that is equal to alpha times the T1 image of V. And it turns out that with this additional operation, this actually is a vector space over F. One more remark that I should add at this point, a notational remark, is that do not forget that in Herstein, in this book, we are following this notation. That is, ordinarily we would write the image of V under T1 like this. But here we are writing the argument first and then the function. Okay, so do not get confused. Just reminding you of that. But in this chapter, we are going to be concerned with not in general V and W, but rather a special case, namely this case where V is equal to W. So that now we have this. So just like the general case, this is also a vector space over F, but now we can define, due to the same vector space in both the places. Due to that fact, now we can define an additional operation. Namely, we can multiply two elements T1 and T2. How? Let's see. Suppose these also I write as T1 and T2, but now they are in this somewhat more special set of homomorphisms, namely homomorphisms from V into itself. And the product of T1 and T2, of course I want this to again be an element here, so I want it to be a function which maps V into V, and I define it like this: V T1 T2 is V T1 T2. So that means on V I first apply T1. So that is going to give me VT1, which is what? This VT1 is again a vector in V. And on that I then apply T2. And it makes sense because we are not going outside of V, we are staying inside V due to these two vector spaces being the same. So, and you can see that this is actually nothing new. This is our simple function composition. That's what it is. But now, in order to claim that this new operation is actually an operation on this set, we need to show that this T1, T2 is a vector space homomorphism. That we have to show. Okay, so let's just do that first. You may be wondering why I have started writing things on this side. That's because once these initial parts are over, we will sort of formally start the things from here. So now our aim is to show that T1, T2 belongs to home V, V. What do we need to show that? Like how we show a function is a vector space homomorphism, it has to preserve vector addition and multiplication by scalar. So those two things we have to show for T1 and T2, T1, T2. So let us start by considering two vectors V1 and V2 in V, and let us also, because we will need it, let us also consider a scalar alpha in the underlying field. So first we have to show that T1, T2 respects addition or preserves addition. So let's see what happens when we apply T1, T2 to the vector V1 plus V2. By definition, first we will apply T1 on that, and then on the result we are going to apply T2. That is the meaning of composition. And before I progress in this calculation, let me also show you just one thing for why Herstein has decided to, this is something that we have already talked about at length, but still let's see once more. Why does Herstein insist on writing the argument first and then the function? It's because when you do that, then composition follows the natural order in which it is written. So if you write T1, T2, that really means first apply T1 and then T2. But this is not the case if you write the argument on that side. Okay, so that is why, that is one advantage. But there is another advantage also. We will realize why this is, it's not just simply because of this, but there is something related to matrix multiplication. We will see those things, okay, they are coming. So now, because T1 respects addition, since T1 is a homomorphism, so this is V1 T1 plus V2 T1 T2, and T2 also respects addition, and V1 T1 and V2 T1 are both vectors in capital V. So this is again equal to V1 T1 T2 plus V2 T1 T2, and that is equal to, once again if you apply this above definition, you are then going to get V1 T1 T2 plus V2 T1 T2. So yes, T1 T2 does respect vector addition. Now next we have to show that it respects scalar multiplication. So next let us calculate alpha V1 T1 T2. Again, by definition of this operation, it is alpha V1 T1, and on that we are going to apply T2. Now T1 respects scalar multiplication, so this is equal to alpha times V1 T1 T2. And now note that this V1 T1 is a vector in V. So this is a multiple of that vector by the scalar alpha, and T2 being a homomorphism itself will respect this scalar multiplication. So that's why this will be like this. V1 T1 T2. Okay, and that is just simply I can use another bracket just to show that the alpha is waiting outside. So whatever is happening inside will happen first, and then alpha will be multiplied with that vector. But inside we can apply our definition. So this will be V1 on which T1 T2 has been applied. So that's how applying T1 T2 on alpha V1 is the same as applying T1 T2 on V1 and then multiplying by alpha, which is just preservation of scalar multiplication. So that is why this new function T1 T2 is also in home V comma V. So we have just simply achieved the fact that this is a binary operation, just like the addition in home V comma V. This is another binary operation which we are going to call multiplication for reasons that will be clear now. Okay. This is not the only property that this new operation has. It has other familiar properties. So let us start by writing those properties here. Now we start from here. V. So I'm not again going to write those things. Okay, let V be a vector space over F. We understand that those things are there in the background. So instead we write like this. We know that the set is a vector space over F, and the adjacent operation means this one, has the following properties. Besides the set being closed under that operation, these are some other properties. So in these properties, we will need three elements actually. And one scalar. So for these things, now I need to clean that part. But we have seen what we have done here. Nothing much. We have just shown that T1, T2 again belongs to home V, V. The addition that we already have on home V, V, you will see it interacts very well with this new multiplication, which actually is nothing but function composition, like this. Number one property, T1 plus T2. So this plus is already the plus we have here, times T3. So this multiplication is the one we defined there. It turns out that this is equal to this. What we would normally expect to have, that is what we are having. A right distributive law. Multiplication distributes itself over addition from the right side. And there is a left version also. T3 times T1 plus T2 is equal to T3 T1 plus T3 T2. If you want to see why these are true, you just have to apply the left hand side to an arbitrary vector from V, and you just apply the definitions of these operations. You will see that it will be equal to the image of V under this. Or perhaps I should show at least how this is true. One of them we see, then it will be okay. So let me just simply calculate this. The others are going to be similar. So what are you going to write next? You apply the definition of this product, because after all this entire thing is a product. So this is just function composition. So you first apply T1 plus T2 on V, and on that you apply T3. Now applying the definition of plus, which is the addition on home V, V. This V on which you are applying T1 plus T2, this is just VT1 plus VT2. This is the meaning of this plus. And then T3. Okay. Next, what will you do? Next, you have to actually apply the fact that T3 is a homomorphism, and hence it will respect addition. Because do not forget that VT1 and VT2 are both vectors in the space V, on which T3 is a homomorphism. So that's why VT1 T3 plus VT2 T3. And next you apply the definition of our new multiplication. So that gives you V1, V T1 T3 plus V T2 T3. And then here again you use the definition of our addition, but in the reverse order. So that gives you this. So because these two functions behave identically, they have the same effect on any vector, so as functions they are the same. That is why you have this equal to this. A similar argument will give you this identity. But there are other properties also. For example, our product is associative, which is nothing surprising. This is something that we already know because our product is simply function composition, which we already know is associative. So that's why this is it just looks like this. And there is a fourth one also, and this fourth one is going to involve this alpha. It turns out that if you take the product T1 T2, okay, and then multiply it by alpha, that is equal to alpha T1 times T2, and that is also equal to T1 times alpha T2. So although you may not write T1 T2 equal to T2 T1, that may not be true, as you already know that function composition in general is not commutative. But you can write alpha with any one of them, or you can write alpha outside also. So note carefully that among these properties, this only involves addition and multiplication. Okay, that means this is the link between those two operations, and the addition in v comma v and the multiplication we have defined today. This one is also like that. So these two are the two distributive laws linking addition and multiplication. This one says that our multiplication is associative. So this one has only one operation, that multiplication itself. This law on the other hand links multiplication with scalar multiplication. Okay, so these are some of the properties that this new product or multiplication has if the other operations are also considered. These other identities can also be proved like this. I leave that thing to you. This of course you do not need to prove. This one needs to be proved. But you can just simply go with the flow without making mistakes, okay? Always being careful what you are doing and what each symbol at each stage means. So once you do it carefully, you will see that yes, this is also true. Now, there is a very special element in v comma v. While going through examples of vector space homomorphisms, you may remember that we started with two extremely easy and kind of boring homomorphisms. One of them was the zero homomorphism, which maps, say you have, there we had different vector spaces, right? V and W over the same field, of course. The first one maps every vector v of v onto the zero vector of W. This is a homomorphism, the zero homomorphism. There was another one, which however were defined only for this type of situation, and it was the identity map. This also turns out to be a homomorphism, and so being a homomorphism, it will be an element in our space. Now what happens if we take I in place of T1 and in place of T2? What is it that we are going to get? Let's see. In this fourth property, if we once take T1 equal to I and then take T2 equal to I, what is it that we are going to get? Suppose we take t1 equal to I, then we get I times alpha t2. Now you know that this identity function actually is, it has no effect when you take its composition with any function, because our multiplication is simply composition. So that is why IT2 is simply T2. And this of course is just simply alpha T2. So we are not getting anything new from this part, but this is something we see. On the other hand, if you take I in place of T2, then what is it that you get? You then similarly get this one will be alpha T1, this one also will be alpha T1. However, this one is T1 times alpha I. Okay. Now you concentrate on this and you concentrate on this. These are general identities, right? No matter what T1 you have here, this is going to happen. Similarly, no matter what T2 you have here, this is going to happen. So if you just simply take T1 to be anything, suppose some T, then you have alpha T equal to T alpha I. And similarly, here also you have alpha T equal to alpha I T. You may be a little confused in the fact that I have taken both T1 and T2 to be the same thing. Okay, because here once I considered T2 to be I, and here here I have considered T1 to be I, and here I have considered T2 to be I. But in doing so, I obtained some result which is true for all T1, not just that T1, for any homomorphism. Here also, for any homomorphism, I have obtained this identity. So I can consider that any homomorphism to be that same thing. Okay. So now these two equations give me what? Alpha I t is equal to alpha t, which is equal to t alpha I. So these special homomorphisms, alpha i's, in our space have the property that they commute with every element. Commute in the sense that we have one multiplication also, right? Addition is commutative, okay? But the multiplication in general is not commutative. Why, we will see. But these special elements commute with everything. So this is another fact about this entire system. Now that we have the properties of this system, let us look at what the system has become. On one hand, let me first write the symbol. on one hand, this is a vector space over F. This is something we already know. Okay, we already knew before doing all these things. On the other hand, now watch this carefully. What is it that we did with the multiplication? First, we showed that this set is closed under our multiplication. Next, we proved that two distributive laws are true. The one that I wrapped up here and this one, where we have addition. And what is that addition? That addition is the addition you have in the vector space. So the set is closed under multiplication. The two distributive laws are true, and additionally the multiplication is also associative. And when those things happen, we call such a system a ring. Okay, you recall the definition of a ring. It's a ring. It is a vector space, but additionally it's also a ring, and the plus operation is common to these two structures. The vector addition turns out to be the addition of this ring structure that this set has. What else is true? This is true. It's a property that links the two other operations, namely the scalar multiplication that you have in the vector space and the multiplication that you have in the ring. And additionally, something else is also true. The vector space, or I should not say the vector space, but now I am coming to the ring aspect of this thing, has a unit element with respect to the multiplication, of course. Okay, so it's not just any ring, it's a ring with a unit element. It's not necessarily a commutative ring, although we haven't seen non-commutativity between two homomorphisms, but we will see. Okay, those things are coming. However, despite possible non-commutativity, there are some elements which commute with all the elements of the ring. So equipped with these two kinds of structure, this set becomes very useful, and it is the set that is going to give rise to what we know as linear algebra. And in fact, the name algebra itself is going to be a kind of structure. Just like we have groups, rings, fields, vector spaces, like that there is another structure whose name itself is linear algebra. The subject is also called linear algebra, but such structures are also called algebra. Okay, so now next we are going to see that definition. So this is where properly all the things begin. So we have to understand this definition carefully. An associative ring A is called an algebra over a field F if A is a vector space over F such that something else is also true. and that something else will be in the pattern of this fourth property. Such that for all elements A and B in A and scalar alpha in F, alpha AB is equal to alpha A times B, that is equal to A times alpha B. Now let us read the definition once more and then we will decipher it. What is the author saying here? An associative ring A. I know that we started with this set as a vector space and then we brought in a multiplication which made it a ring, but the definition is given in terms of a ring. Okay, it's not going to make a difference. So an associative ring A is called an algebra over a field F if A is a vector space over F such that this happens. Okay. Now there is something which one should I address first? Let me just first say something about this associative ring. If you go back to the definition of rings in Herstein, there was one part which is very easy to forget. Herstein defined a ring, the way he defined we already know all those things, okay. But at one point he mentioned that it is not actually necessary that the multiplication in a ring be associative always. That means it is not necessary that if you have 3 elements in a ring, in a general ring, this is actually not necessary. It may not be true, but the structures in which this is true are called associative rings. Actually, that is the reality of these structures. But non-associative versions of rings are also available. Okay, I'm not going into examples or anything, but they exist and they are also studied. They are also very important. Because in this book we will have no occasion to consider non-associative rings, that's why we omit the associative, this word, and simply call our structures rings. Ideally we should call them associative rings, but because we are not considering non-associative rings at all, so that's why we just simply have decided to call these itself rings. But anyway, so there is no need to be scared of this associative word. You can just say a ring. Okay, that's it. So a ring A is called an algebra over a field F if A is a vector space over F. Now let's come to this thing, the link between these two structures. So A is there. We have started with A being a ring. So already there is an addition and a multiplication. Okay. And now we are saying that it's a vector space over F. So just to distinguish between the two types of multiplication, I am going to temporarily denote the scalar multiplication by star. Are these two additions different? The definition actually says nothing about that. Okay. but actually they are the same, although the definition does not indicate that fact. It just simply says that this ring should be a vector space over the field F. But whether the addition should be or should not be the same as this addition, the definition doesn't say anything, but actually it is the same. Okay. Such that this additional thing is true. That is, if we are taking any two elements from the ring or vector space, anything you can call it, because it is both, and take a scalar from F, then multiplication by scalar and multiplication are going to interact with each other in this way. Okay. So by what we have seen so far, this is an algebra. And algebra over F. And it's an algebra with a unit element, which in general need not be true, because here in the definition you see no mention of any unit element in the ring part of that algebra. And this algebra is going to be studied. The study of this algebra is called linear algebra. And in it we will also see the other parallel world. Parallel to this algebra, there is another algebra which is essentially the same as this one, whose elements are not vector space homomorphisms but matrices. That algebra is called matrix algebra. It's not a single one. I mean, here when you change V, the algebra is going to change. So there also when you change sizes of matrices, so matrix algebra is going to change. But there is a very deep link between these two things. Okay. And now next, so this is a new mathematical structure. I mean this one, an algebra. So naturally for algebras also we can expect that we have homomorphism, isomorphism, and many things will come, no? Since it's a ring, ideals will also come. So they will be defined just like how we define them in rings, but with the additional condition that those things must also preserve or be invariant under the vector space structure. What this remark means, we will see more clearly when the time comes. Now, because we are going to again and again have to write this, obviously this we cannot keep writing such a cumbersome thing again and again. So instead we are going to consider a new notation which is shorter. In place of this we will simply write AFV, or if we want to suppress F, simply AV, and this is going to be called the algebra or the ring of linear transformations on V. And this word, although we perhaps already know what linear transformations are, but it needs a definition. A linear transformation is just a vector space homomorphism, that's it. I don't know, maybe this is not given as a definition in the text, but let me just write it as a definition. Any element of this is called a linear transformation. On V to indicate the fact that there is an underlying field and what that field is, we also write on V over F. Now here is something I am going to deviate a little bit from this book. So what the author is calling is that any element of AV will be called a linear transformation on V. Fine, that is okay. But I would prefer something else. I would call a vector space homomorphism from any vector space V into any vector space W a linear transformation. But in the special case where the two vector spaces are the same, which is the case we are considering, I would like to call these linear transformations linear operators. And this is not something that I have made up, it's in common use. Okay, in many places you will see that when functions of a kind that is their transformation, something like this, are used which map one set into itself, such functions are called operators. Here we are going to consider linear operators. So instead of calling the elements of this algebra linear transformations, I am going to call them linear operators. And accordingly, I will also call this the algebra or ring of linear operators on V over F. Okay. Now you recall a result from group theory. In group theory, we had one section on Cayley's theorem, right? Which tells us that permutation groups and their subgroups are, in a sense, the only groups. That is, any group can be embedded inside a permutation group. Expressing more rigorously, this just means that if you have any group whatsoever, then there exists a permutation group in which there will be a subgroup which is isomorphic to this any group, this given group. Such a result is true for algebras also with unit element, and that is our first result. So it goes like this. Let A be an algebra over F. When we write over F, it's understood that F is the underlying field. No need to separately write field. That has a unit element, then A is isomorphic to a subalgebra of A V. AB is that AB we have considered just now, this AB. For some vector space V over that same field F. So what is it saying? It says that if A is an algebra whatsoever, then you will find a vector space V such that if you consider the algebra of linear operators on V, okay, then there exists a subalgebra with which this algebra is isomorphic. So it's just like that Cayley's theorem in group theory. Every group is isomorphic to a subgroup of a permutation group. Like that, every algebra is isomorphic to a subalgebra of an operator algebra. So let's now see the proof. Yeah, I will quickly need that part, so let me just clean up a little bit. Operator algebras and the fact that the multiplication in an algebra in general is not commutative, these things are very useful in quantum mechanics. This non-commutativity plays a crucial role in quantum mechanics. Okay, so what is it that we have to do? We have to set up a function of this type. But before we do that, we need to decide what V should be. You remember what we did in groups? In groups, we needed to find a function from G into the permutation group A of S, that is the group of all permutations on the set S. And while starting the proof, what did we take as S? In place of S, we considered the set G itself, and exactly the same thing we are going to do here. In place of V, we are going to consider A itself. Does that make sense? Yes, it makes sense, because being an algebra, A is a vector space over F. It's a ring also, but it's a vector space also. Okay, so we are going to consider, I'm of course not going to write everything formally, I will just show the steps. So our V is A. This we have decided. So now next we have to set up the map. So I choose one input, A from A. What should be my output? Note that the output must lie here. That means the output needs to be a linear operator on V. So what I do, using this A, I define a function TA from V into V like this. Applying TA on any vector V from V, do not forget that our V now is the algebra itself, so it's a vector space also, is by definition VA. Does this make sense? What have we done here? We have used the fact that there is a multiplication of algebra elements because it's a ring. So we have multiplied V and A. Because multiplication is well defined, so for a given V in A means in V, same thing, VA will be a unique element again in V, that is A. So this TA is well defined. Never forget that whenever you define a new map, you must first of all make sure that it's well defined, that it's actually a function, not an arbitrary relation. Okay. So now that TA is well defined, we can next see what else it is. Our next job now is to show that this TA is here. That means TA is a linear operator on V. In other words, it's a homomorphism of V. So to that end, we are going to consider two vectors V1 and V2 in V and one scalar alpha in F. We need to see whether TA respects addition and scalar multiplication. Let's see. What happens when we apply TA on V1 plus V2? By definition, this is V1 plus V2 times A. And now the fact that we have a distributive law is going to help us. So this is V1A plus V2A. Never forget what we are doing. We are in a ring and this is the right distributive law. And by definition, V1A is just V1TA and V2A is just V2TA. So yes, TA respects addition. Next, we apply TA on alpha V1. So again, by the definition of TA, this is alpha V1 times A. But then you remember the definition of an algebra. In that definition, this can be written, in its place you can write this. And V1A is just V1TA. So yes, TA besides respecting addition also respects scalar multiplication. So that's why it qualifies to be an element in AV. So that's why TA belongs to A of V. So fine, we have found a map that takes any element in A as input and gives us an element in A of V as output. Let us give that map a name. Let us call it psi. And what is the definition of our psi? A psi is defined to be TA. Now this is another map. Okay. Is this well defined? Yes, it is. Because for a given input from A, we are getting a unique output in A of V. Unique means for A we are getting this TA. This TA is just one such defined map. It cannot be anything else at the same time. So psi is also well defined. Okay, now comes the somewhat unknown, means we know what it should be, but what do these words mean? Isomorphic to, subalgebra. Remember, we haven't defined them yet. So now is the time. Subalgebra means, say you have an algebra. In our case, we have the algebra A of V. A subalgebra would be a subset, a non-empty subset, on which if you restrict the operations of this algebra, then that subset itself will turn into an algebra. So it's just like the definition of a subgroup, subring, subfield, subspace, just like that. Now, isomorphic means a one-to-one homomorphism. Be careful, in this text, isomorphic only means one-to-one-ness or injectivity, not onto-ness. But it is more common to also include onto-ness in this word, isomorphic. So in other texts, you will more likely get the other meaning, that is, in them, isomorphic means both one-to-one and onto. It's not the case here. A one-to-one homomorphism But homomorphism means what? A homomorphism between two algebras means what? That also we need to see now. Because otherwise, what shall we do with this psi? Our aim now would be to show that it's an isomorphism of the algebra A into the algebra A of B. What did the author say? The author said that it should be a ring homomorphism. So that means we need to check that psi respects algebra addition and algebra multiplication. But at the same time, the vector space structure should also be preserved. That means additionally, psi also has to respect scalar multiplication. So we need to show three things. Psi respects addition, multiplication and scalar multiplication. Okay, so let's do that. Psi respects addition, multiplication and scalar multiplication. Okay, so let us take any two elements C and D. If you want, you can take A and B also, but let's forget what we did above. This is fresh. And for that matter, let me take beta in F. So first we see what psi does to C plus D. By the definition of psi, this is T C plus D. But what is T C plus D? To see what T C plus D is, we take an arbitrary vector V in A, and we at least know that T C plus D is a linear operator on V. That is, it's an element in AV. But what does it do? What is it going to do to a vector V? To see that, we apply Tc plus D on V. By definition, this is V times C plus D, and now forgetting that V is a vector and C and D are algebra elements, these are after all ring elements. So by the left distributive law, we have this. But VC is what? By definition, it is VTC. Similarly, VT is VTD. And now finally, applying the definition of addition in this algebra, this last thing is equal to V on which Tc plus Td has been applied. So the effect of Tc plus D on V is the same as the effect of Tc plus Td on V. So that is why that means Tc plus D is this, and this thing is C psi plus D psi. Is it what we want? Let's see. What is this plus? This is the plus that we have in A, because C and D are elements of A. What is this plus? This is the plus that we have in AV, because C psi and D psi, which are respectively these two, are elements of AV. So yes, psi turns the addition in A into the addition in AV. So it respects addition. So next, let's see multiplication. This is TCD. Again, to see, just like that, this previous calculation, to see what TCD is, on V we apply TCD. So this is V, C, D. Multiplication is associative. So VC times D. But this is VTC, and because we have D outside, this is TD. And finally, by the definition of multiplication on AV, this is VTC/TD. So TCD is TC/TD, i.e. CD psi is C psi D psi. Psi turns the multiplication on A into the multiplication on AP. So it respects multiplication also. And finally, what happens if we calculate this? This by definition of psi is T alpha C. On V, if we apply T alpha C, then we get V times alpha C. So because we are in an algebra, in which algebra? In this algebra. So in its place we can write alpha times Vc, but that is alpha times Vtc, and that in turn is equal to V alpha times Tc. If this last step seems confusing to you, you go back to the definition of scalar multiplication on AV. When we multiply a linear operator by alpha, this is what it means. So, considering the first and last term in these equalities, we will get what? We will get T alpha C is equal to alpha times Tc, i.e. alpha C psi is equal to alpha times C psi. Do not make the mistake of writing alpha psi. Okay, alpha psi has no meaning. The inputs of psi are not scalars, they are algebra elements. So psi respects scalar multiplication also, and hence psi is an algebra homomorphism. But that's not enough. We are expecting psi to be an isomorphism. So now we need to prove that psi as an ordinary function is injective, it's one-to-one. Is it? So one thing we have realized by now, that a vector space homomorphism is simultaneously an algebra homomorphism is simultaneously a vector space homomorphism and a ring homomorphism. But now, one-to-oneness. So because it's a vector space homomorphism, we have already proved that. So to prove that it is one-to-one, it's enough to show that its kernel is trivial, that is, it consists of only the zero vector. So let A, okay, but the kernel will be an element of what space? Namely the algebra A, because it's the domain. So let B in the kernel of psi, considering psi as a vector space homomorphism. But even if you consider psi as a ring homomorphism, there is also a kernel. You see, things can be very confusing. The kernel as a vector space homomorphism, when you consider this one as, is a subspace of A. But at the same time, when you consider the kernel of psi as a ring homomorphism, it's an ideal of A. But anyway, let's not go into those things. So we are now considering psi as a vector space homomorphism or a linear transformation. Then A psi is equal to what? Okay, you should be careful. A psi is equal to what? A psi is equal to 0. What does this 0 mean? This 0 is the zero element in the algebra AV. But what is the zero element in the algebra AV? It is nothing but the zero element in AV as the zero vector or the zero element in AV as the ring zero element. They are both the same, and that is nothing but the mapping from V into V, which maps, I am using 0 to denote the map also, okay, which maps every vector of V onto the zero vector in V. So it is the zero mapping or zero homomorphism. Do you recall what we said when we were talking about that identity mapping I, that we have a zero homomorphism also? That in fact is the zero element in AV, it turns out. Okay. So A psi is what? TA. TA equal to 0. So TA is the zero map. It's going to map everything into 0. But now do not forget that our algebra A, I need space. Our algebra A is not any algebra, but it has a unit element. That fact now will be necessary to go forward. Without that, you cannot prove that it's an isomorphism. Such algebras which have unit elements are also called unital algebras. So choose the unit element. If you want, you can write 1 here also. Then ETA is equal to E0. You do understand that here 0 means the zero function. Now ETA by definition is what? EA, and E0 is 0. This 0 is the zero function and this 0 is the zero algebra element. And now use the fact that this E is actually a unit element. So EA is equal to A. So that is why A is equal to 0. So the only element in the kernel of psi is the zero element. That is why psi is injective or one-to-one. And this makes psi an algebra isomorphism of A into A of V. Now here comes the next thing. this is our A, this is our A of phi, and A has found through this map psi a sub part of A of phi with which it is isomorphic, algebra isomorphic. But is this a sub-algebra of A of phi? Actually it is, and it can be proved that the image of any algebra under a homomorphism, not necessarily isomorphism, even for a homomorphism, is itself an algebra. In this case, it's a sub-algebra of A of phi. Just like images of groups are groups themselves, images of vector spaces are vector spaces themselves, just like that. This part I am not going to do. Okay, it's extremely easy. So that's how A has found an isomorphic copy of it inside A of phi, or in another language, A has been embedded inside the algebra A of phi. So in this sense, the algebras AV and subalgebras of them play a universal role, the kind of role that permutation groups and their subgroups play in group theory. Any algebra whatsoever can be found as a subalgebra of one of these. Okay. And the next thing, we are not going to go any further today, but let's see what is going to come next before we end this video. The thing is that the algebras AV that we are going to consider here in linear algebra primarily considers not just any vector spaces but the finite dimensional ones. And when that restriction is there, it turns out that every element of AV, that is every linear operator on V, satisfies a polynomial over F. And from that fact come those things, characteristic polynomials, minimal polynomials. So it gives us a way of probing deeper into the subject. So that's how the next part is going to come. So that's just it for tonight. So let's see what comes in the next part. This is very interesting, and many things from ring theory are going to be used, and in particular that fact that every ideal in a Euclidean ring is a principal ideal. That fact has an application here in the form of every linear transformation having a minimal polynomial, those things. Okay. So tomorrow also we have our upload means in the community section, of course. I think tomorrow we have to again solve group theory problems from Lee's book. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.